Okay, it looks like most of us are finishing up, so let's go ahead and discuss our bell ringer question for the day. You have two different objects that you are to sketch in your notebook. Who feels confident they can go to the board and show with the red pen where that transfer of thermal energy is taking place? Jillian, you want to give it a shot? Use the red pen. Show us where thermal energy is moving to. Why don't you just borrow this one for now then? Oh, hold on. Let me unfreeze you. Thank you. Okay, let's take a look at what Jillian did on the board with the thermal energy arrows. And very quickly, thumbs up, thumbs down. Do we agree? Do we have a similar sketch in our notebooks? Thumbs up, yes. Thumbs down if you did it differently than how Jillian has shown us. Wonderful. Who can explain why that's correct? Why did we draw arrows going into the house? Brynlee.
Because the heat always goes to, it's always trying to go towards the place where it's not, because, equilibrium.
Excellent. What do we mean by equilibrium? What does that mean? AJ?
When thermal energy tries to enter a place where it's not certain.
You got it. Thermal energy is always going to go to a place where there's less thermal energy, trying to achieve equilibrium. What do we think these little red blocks are that she did at the front of her arrow? We see the red arrows, and then we see some little blocks that she sketched. What might those be showing us? Daisy, what do you think?
It's where the thermal energy stops because the house has insulators.
Because the house has insulation in it. What do we know about insulators? What do we know about insulators? It explains why Jillian showed that that is blocked there. Ella?
Insulators don't allow for heat transfer.
Good. Insulators are not very good for heat transfer. They're going to block or slow down how quickly that heat is moving. Very good. What's the opposite of an insulator?
Conductor.
Matthew?
A conductor.
A conductor. So if an insulator blocks or slows it, what does a conductor do when thermal energy hits it? TJ?
Allows thermal energy to pass through.
Very good. It allows that thermal energy to pass all the way through. What we are going to do is a very, very quick review. Yesterday when you left class, you did some exit questions on conductors and insulators, and I want to make sure that we have a good understanding of that before we start with today's new topic. So if you look at the plastic bin at your table, you need to pull out one of the index cards that has an I on one side and a C on the other side. There should be enough for everybody in there to have one. Make sure you don't grab a blank one. There should be two letters. What do we think that I stands for? Insulator. What do we think the C stands for? Conductors. Wonderful. I'm going to ask you a couple of very quick review questions. All I want you to do, hold up your index card. The C is for conductor. That needs to face me if that is your answer. The I is for insulator. That needs to face me if insulator is your answer. So, first one. Which of those two things is going to allow for the easy transfer of thermal energy? Easy transfer of thermal energy. Hold up your choice facing me. Excellent. Correct answer was, everybody? Conductors. Wonderful. Next one. Which one do you want to have in the walls and roof of your home during summertime? Which one do you want in your walls and roof of your home in the summertime? Carson, flip your card correctly. Thank you. Excellent. 100% again. What's the correct answer? Insulator. Next one. What do you want in the walls of your home during the winter? Man, I didn't trick anybody. You still got it correct. Answer was? Insulator. Why do you want an insulator both summertime and wintertime? Why is an insulator good no matter what season it is? Alyssa?
Because it keeps thermal energy both in and out.
Good. Good. It's going to keep the thermal energy in when you want it to be in, and it's going to keep it out when you want it to be out. What season do we think this is showing based on that?
Summer.
Summer. Excellent. One more question. Copper, aluminum, and zinc are most likely examples of what? Wonderful. Conductors. What do those things all have in common? They're all metals. And what do we know about most metals from our last unit? AJ? They are all pretty much good conductors. Excellent work. You may put cards back. I feel pretty confident we're ready to move on. What do you think? Do we have any final insulator conductor questions? Excellent. Who would like to read our learning target for today? Brynley, thank you.
I can explain the difference between conduction, convection, and radiation, and identify examples of each type of heat transfer.
Thank you. What words up there do we not know yet? What stands out as something we have not discussed? Might be a new term we should learn. Jackson.
Convection.
Convection. We don't know convection yet. What else do we need to know that's up there? Carson.
Radiation.
Radiation. We don't know radiation yet either. Jim.
Conduction.
Conduction. So that's 3 new words. What other science words up there do we need to know? What else should we be able to understand before we can do those 3 words? Nicholas.
Heat transfer.
Heat transfer. Wonderful. What could we also call heat transfer? Thermal energy transfer. Wonderful. If you look at our learning target, those 3 words you pointed out, conduction, convection, and radiation, are all the 3 types of heat transfer that we are going to focus on for today. Do we know anything about those words to start? Have we heard them before? Does it make us think of anything in particular?
Conduction is like conductor.
Okay, conduction reminds us of the word conductor that we've been talking about. Carson.
Radiation.
Okay.
I've heard it before, and it reminds me of the word like contaminated or like exposed to.
Okay, we've heard the word radiation before, and we typically hear it with the words exposed to radiation. Alyssa.
Radiation also, in the essay we did, there were a couple paragraphs on it.
Okay, so in our writing piece that we did on the climate change, we saw the word radiation come up in a few different paragraphs there. What we're going to do today is take all those things that you are correct about. I know we've heard these words before, and we're going to make sure we understand what they mean and how it applies to the penguin home design we did. And then next week, what it means for our ocean currents and global climate. So we are going to start today with a quick foldable that's going to summarize all of these 3 new vocab words for us. So when you get it, make sure that you have a glue stick and scissors. There's extras in your bin if you need them. Okay, when you get your paper, your final product should look like this, which means you are going to make a cut with the scissors along the dotted lines. There's 2 dotted lines. And then you're going to fold them all over. So you have a triple foldable that can then be glued into your notebook page. You got it, Jim? Cut the 2 dotted lines. Then they'll be folded over so that you can glue the blank backside straight into your notebook. Okay, once we are glued in and ready to go, we're going to do two things for each of those words in our foldable. The first thing we need is a good definition for each word. And then we're going to take a look at a couple of demonstrations in class for each of those three types of heat transfer that you will sketch in that foldable. That'll give you an example using pictures as well as the definition using the words. So we're going to start with our first word, which is conduction. Who would like to read our first definition for us on conduction? AJ, thank you.
The way thermal energy transfers from one substance to another by direct contact.
Very good, thank you. We're going to write this all on the left side of our first foldable. So when you open that door for conduction, we're going to write down our definition. As AJ said, this is the way that thermal energy transfers by direct contact. And those are our key words. We need to make sure we underline these in our definition. By direct contact. Is that one yours, Jim?
What's up, Mom?
Thank you, Matthew. That's very nice of you. There you go.
Sir, do you want me to put this in this for now, or do you just want me to?
You can just hold on to it, tuck it in the folder, and we'll glue it into your notebook tomorrow. Okay, so when we talk about conduction, we're telling us that thermal energy transfers from here to here, but there has to be direct contact made. The heat source, the one that has the most thermal energy, is directly touching the other source. So I need a couple of volunteers that are going to come up and help us show what conduction looks like. Luke and Ella, come on up. Okay. What do these two things have in common? They're spoons. But what's different about them? What's the obvious difference, Carson?
One's metal, one's plastic.
One's metal and one's plastic. What can we then also infer about our vocab terms we've been talking about? Another big difference between the two. Emma?
One's an insulator and one's a conductor.
One's an insulator and one's probably a conductor. Which one do we think this one is?
Insulator.
Insulator?
Conductor.
Conductor. Which one would you like? You got this one. Now they're going to stand over here, and I'm going to give each of them an equal-sized ice cube to put in the spoon, and they are going to hold on to that ice cube in their spoon. If I can pick it up. Right up here at the front of the room for a minute. So face the class and make a fist around the handle so you're holding it nice and tight and try to balance that ice cube. Any predictions about what's going to happen in about 1 minute? Nicholas, what do you think?
Ella's is going to melt since she has a conductor.
Okay, we think Ella's is going to melt because she's holding a conductor. What do we think is going to happen to Luke's ice cube? Carson?
It will stay because it won't be that cold because it's an insulator.
Okay, so we think it's going to stay cold because he's holding something that's more of an insulator than the spoon Ella has. Alyssa?
I think it will still melt, but it will melt slower because it's an insulator, but also it's exposed to all of it.
Which means what?
It'll still melt because of thermal energy.
Thermal energy from where?
The room.
Excellent hypothesis. So Alyssa's telling us, even though we think Ella's will melt first because she's clearly holding something that's a conductor, if Luke stands up here long enough, eventually his will melt too, because even though he's holding an insulator, a plastic spoon, there's still thermal energy in the classroom. And where is all this thermal energy in the classroom going to try to go? To these ice cubes. Wonderful. If Ella's holding a conductor, what does that mean? We know conductors transfer, but where is their thermal energy coming from? How's it going to get to the ice cube? Ella's not touching the ice cube. She's touching the spoon. Leah?
Like the air.
Okay, some of it's going to come from the air around us, right? We know it's warmer in here than the temperature of an ice cube. Where else? Alyssa?
From the heat coming from her hand.
From her hand, because your body heat is obviously warmer than an ice cube too, right? So she's got two sources of thermal energy making their way to the ice cube, but Luke only has how many? Just the one from the classroom. Can you give us a quick report? Ella, what do you notice about your ice cube?
It's melting. There's water in the spoon.
Okay, so we see a puddle of water in the spoon, which is evidence of melting. Luke, can you describe yours?
It's the exact same as when I got it.
Exact same as when you got it. Do you notice a big puddle yet?
No.
Any sign of melting?
No.
No. Ella, yours looks like it's almost completely melted already. Yours is getting pretty small. What do we think would happen 1 minute from now? Brinley, what do you think?
Ella's would be completely melted and his might be just a little bit.
Okay, so we think if 1 minute were to pass, we're already halfway gone after our first minute, this one's probably still going to look the same. Which means we just saw an example of conduction. There is direct contact between the hand, the conductor, and the ice cube. We can see that there is clearly something else at play with Ella's spoon. These are the same size ice cube, the same kind of material, just a different insulator versus conductor. Clearly that one's melting faster. That means there is a heat source and it is being transferred here and not here. So we are ready to sketch this demonstration on the right side of our foldable. Thank you. You may both dump them, put spoons on the counter, and go sketch yours as well. So we have two spoons. I would make sure I labeled my spoons because I want to know which one is the conductor and which one is the insulator. And we're sketching that at the end of our time, we've still got one solid ice cube and one that's melted. All right, I see an excellent use of labeling going on, identifying which one's plastic, which one's metal. And if I were you, I would also grab a red pen or pencil and show where that thermal energy is being transferred from. Where should your arrow be? Going from what to what? Where's the thermal energy in that demonstration we did? It's mainly found where? In the air and the hand. So all of that thermal energy should be pointing towards your ice cubes. Very good. Okay, if you take a look at the front of the room once you finish your sketch, we've got some demonstrations started for our next two terms. We have convection and radiation left. So we're going to start with convection. We need that definition. So who would like to read convection for us? Don't volunteer all at once. Jim, thank you for volunteering and being brave today. Convection.
The rising and falling of liquids and gases due to differences in density, which are caused by differences in temperature.
Excellent, thank you. Convection, second one. Okay, what do we instantly notice about this definition? What were the key words for conduction that are no longer in this one? What did we underline that was very important in conduction, but is nowhere in this definition for convection? Stephanie, what did you notice?
In conduction, we underlined direct contact, and we don't have that.
Good. So we already noticed one major difference between the two, right? Conduction requires direct contact between the heat source and your other source. In convection, we don't have direct contact anymore. This one has to do with density. We know things are going to rise or float, and other things are going to sink or fall. So we need to think back a couple of units. What do we know about the density of things that rise or float to the top? What do we know about their density? Friendly?
It's below 1.
Below 1, which means what in terms of density? You're correct. More or less dense than its surroundings?
It's less dense.
Less dense. Things that rise or float must have a lower density than the other things around them. But if they're sinking and falling, we know what about their density then? AJ? It's more dense. Now temperature has something to do with density. Things that are warm versus things that are cold or don't have as much thermal energy are going to have a big difference in density. Which of those two do you think is going to be less dense? Warm or cold? Which one's going to be less dense and typically rise? What typically rises? Melissa? The one with more thermal energy. How many of us have heard the saying before? Heat rises. Or warm air rises. Where'd we say most energy in a home is lost? The walls and where? And the roof or the attic, which tells us that heat's probably rising. And it is because it's less dense. So I am going to have you guys come up and stand closer to this demonstration. So you may come up, leave your notebooks there. You'll need to be close enough to see what's happening. We're going to use some blue and some red food coloring to try and take a look at what happens to things that are warmer and colder. Where should I put the blue coloring if I want it to be in the cold spot? Yes, next to the ice. Wonderful. So again, you're going to kind of want to squat down so you can see from the side view to see where our blue food coloring ends up. Where did it appear to go first?
The bottom.
It sank to the bottom. Where should I put the red then if I want it to indicate where there's warmer conditions? Above the flames.
And it stays up.
Okay, now if we are squatting down to kind of see from the side what happens, we're going to start to notice something happens to the blue, something's happening to the red. And if you're down here, you should start to see where are we seeing things rise to the top and where are we seeing things sink to the bottom. What color is sinking to the bottom?
Blue.
Blue. What's happening to the red?
It's rising.
It's rising. So when we put the drops of food coloring in, they both sank right away. The blue stayed at the bottom, but the red is starting to mix and rise up on this side. Where else do we notice the red and the blue moving to? Emma? The middle. Why? What do we know about thermal energy and where it's going to try to go? Leah?
Equilibrium.
Equilibrium. What's that mean?
Try to make the temperature even.
Good. It's going to try to even out the thermal energy so it's the same everywhere, right? If you look from the top view now, you can see from the top, the blue is clearly at the bottom of the pan, right? But cold doesn't move, right? Why is the blue moving if we know cold doesn't move itself? Because cold is not energy. What could possibly explain that? Jillian, what do you think?
Because the cold is like trying to get to the heat, and because the heat's
Is cold ever trying to go anywhere?
no, because it's not energy.
No, because it's not energy. You got it. So where is or what explains why cold is moving then? We know cold's not an energy. What's making it move then? Leah?
The heat is pulling it.
The heat is pushing it, right? Because where's all the heat going to go to?
The ice.
To the cold, because you told me yesterday when we looked at those penguin houses we built, all of that heat's going to try to achieve equilibrium. If it moves this way, you can't have all the water end up over here and nothing here, right? It's not going to make a wall on its own. It's going to push this way, which forces that blue and cold towards the heat. But what's going to happen when our blue or cold gets over here? Because now it's above a candle, right? What's going to happen when the blue does make its way here?
It's going to get hot and going to keep going in a cycle.
You got it. And you just explained to us what a convection current is. If you have cold dropping because the heat's forcing it down and over, that cold's going to get to the warm side and it's going to get heated up, right? So once that heats up, it's now going to rise. It's going to move out towards the cold, and you're going to get a constant cycling of the thermal energy. Now, if we're talking about ocean currents, which we're going to start next week, this also kind of explains ocean currents. What part of the planet is probably warmest with warm water?
By the equator.
By the equator, you got it, gentlemen. Down here. If this is the equator and it's heading out towards the ice, what might this be representing on the planet?
Antarctica.
Maybe, or the Arctic, right, one of the poles. So if we take a look at this, it kind of explains to us how these ocean currents are moving. So we're going to keep that in the memory bank for next week. But we can all head back and sketch our results now for convection. So we're going to sketch our cake pan that we just saw. If we had a cake pan set up with some candles down here and a bag of ice down here, here's our water. We've got our hot and our cold source. So we're going to use our colors to show what that looked like. We noticed that all of this red from our food coloring started to rise and make its way towards the cold, because like you said when we were standing up here, we know thermal energy tries to go to places there's not as much thermal energy. And when that happens, it's going to push all of the blue droplets towards the bottom, and they're going to be forced back over to this candle side. That means that every time new warm water is pushed over by the ice, you get a cycle that we call a convection current. Those currents are going to keep going and circulating because the different densities make it constantly move. Got some good artists in here. I'm kind of impressed with some of these sketches I'm seeing. And then we have our final kind of heat transfer. What's our third and last one? What's our last one, Ella? Radiation. Who would like to read radiation for us? TJ.
Radiation, the transfer of energy in the form of electromagnetic waves.
You got it. Transfer of energy in the form of waves. And again, what are those words we underlined in conduction that we no longer see in radiation? Brinley.
By direct contact.
By direct contact. We don't see that anywhere either. So if we're trying to understand the difference, we know conduction requires direct contact. The source of thermal energy is directly touching the other source. In convection, we know that has to do with different densities. It's going to cause things to rise and fall in cycles because of different densities. And lastly now, radiation is when that energy moves through these invisible waves. Some of you said you've heard the word radiation before. Do we remember where we've heard the word radiation used? Where are places we've heard that word or it makes us think of radiation? Jillian.
Like our heat essay that we did?
Okay, in your the Gates writing piece?
Yes.
Climate change. We heard the word radiation a lot. Where did that radiation come from? Do we remember from the article where it came from? You had a different one? Alyssa? The sun. So we know radiation can come from the sun. Good. What else, Leah?
From your phone.
From phones. We've read articles and we've heard things about possible radiation from your cell phones. Carson?
I was watching a show on Chernobyl.
So radiation, when we talk about the nuclear power plants, when there's problems with some of that nuclear energy. Very good. Brinley, where else have we heard it?
Well, like when I think of radiation, I just think of heat in general.
Okay, you think of heat in general. Ella?
When I think of radiation, I think of like the weather.
Okay, you think of the weather. They might have used that word before when you hear the weather report. Luke?
I think of uranium.
You think of uranium, some of those other elements we've discussed. Jillian?
I think of like when machines like go out and they give off stuff like that for the environment.
Okay, excellent. So we've all heard the term before. And now when we look at the definition, we know it has to do with energy being able to move or be transferred through invisible waves. There's no direct contact. It doesn't have anything to do with density. We've set up an experiment to kind of look and see what is this concept of radiation. Let's see. Emma, come on up here. You're going to report to the class. I want you to hold your hand over this ice cube. What's the air feel like?
Cold.
A little chilly, a little warm.
Yeah.
Nothing real obvious that stands out, right?
Yeah.
Okay, now pass your hand over. Don't hold it under the light, but pass it through back and forth a few times. What do we notice about it when we're over this ice cube?
That's warm.
That's warm. Where is all of that heat coming from?
The light?
From the light. Is the light touching the ice cube?
No.
No. Thank you, Emma. You may have a seat. So Emma just told us the temperature right here feels very, very, very different from the temperature under this heat lamp. We're not touching. It's not direct contact, so this cannot be conduction. I don't see rising and falling of liquids and things because there's really nothing to do with density going on. This has to be radiation, but how is the heat getting from the heat lamp to that ice cube? AJ?
It's going through the invisible waves.
Those invisible electromagnetic waves, you got it. You can't see it. It's hard to see. But we can tell that something's different. We can tell there's more thermal energy here because if we look at the ice cube here that's left out with no heat lamp and this one that's under a heat lamp, this one's clearly melting faster. Brinley?
Is radiation, would it be radiation like when you go outside and you see like the blacktop and you can see like the waves?
That is an excellent example because what causes that blacktop or sidewalk to get so hot?
The sun.
The sun. Is the sun touching the sidewalk?
No.
There's no direct contact, right? Do you see the sidewalk rising and falling? No. Which means, how is that heat actually causing the sidewalk to heat up? Which form of heat transfer must it be? Radiation. If you notice something getting really, really hot and there's no direct heat source touching it, no direct contact, and there's also no rising and falling in motion and movement, odds are it's radiation. AJ?
It's like in the movie Holes when Mr. Sturge is turning back because those crystals and the far sheets, he can see the radiation from the ground.
There you go. I have not seen it, but I trust you. You're right. That is another example of where you might be able to tell it has to be radiation. Excellent. Leah, come on up and give us a quick description. The difference between that ice cube and this ice cube.
That's mostly water, and that one's more ice cube.
This one's mostly water, and this one is, what'd you say?
Ice cube.
More ice cube than water. So we have our third demonstration we can sketch the results for. when you have a direct heat source radiating light or heat, it makes sense why that ice cube would melt faster. There's more heat applied here than there is over here. Now, who's feeling super smart today? Who can connect this to our last units we've done? Eventually, that whole ice cube's going to melt. What's going to happen to our puddle if I left this light on and it was just the puddle there? Luke?
It will evaporate.
It will evaporate. You got it. Which means it's going to turn from what to what? What state of matter to what state of matter? TJ? You got it. You guys are just impressing me all around today. Okay, once you finish your final sketch demonstration, you are finished with the foldable, and we are going to do one last activity for the day. So I will see, when I see all pencils down, that we are ready to begin that activity. You should be able to explain to me the difference between conduction, convection, and radiation. Are we starting to get a few ideas about what the difference is? Wonderful. What's the second part of the learning target? Who wants to read that last sentence or the last part of that sentence for us? Emma, thank you.
Identify examples of each type of heat transfer.
Wonderful. Now that we've discussed them, we wrote down a definition, we looked at some demonstrations and sketched what those demonstrations look like. We're ready now to move on and discuss some examples of each kind. This was a demonstration example, but it's not often that you're going to sit at home playing with a heat lamp on an ice cube, right? I mean, I know it sounds like a great Saturday night, but we want to know what all of this means for real events in our real lives that we see day to day. So I'm going to pass out a group of little cards with pictures to each table of 4 of you. This table, all the way down, is working together today as one group. So you guys are only going to be at this table. You have nothing to do with that table today. This table is all working together over here. So again, you're going to have nothing to do with that side today. At each table, you should see 3 posters. One is labeled radiation, one convection, and one conduction. With your table of 4, I'm going to drop off a baggie that has example cards that you will need to get up as a group and walk up and down your posters, correctly placing each example on the poster that you think it fits most accurately. Make sense? Mm-hmm. At the end, when you have placed all of your cards, you're going to go back to your seat. You guys are going to, for example, look at your radiation poster, and we're going to compare with the other side of the room and see if we got the same answers or not. Okay? So when you get your baggie, the 3 of you are going to work together with this baggie. The 4 of you will work with this one. The 3 of you will work with this one. Look at your cards, get up, and place them on the correct poster at your table.
Yeah, because you're touching it.
How do you know it still has to do with density?
Because it's going in a cycle.
Okay, so you see a cycle, right? What's probably the arrows going up indicating?
Heat.
Heat. Why? What do we know about the density of heat? Things that have a lot of thermal energy.
It's going to rise.
That it rises. So this is probably what kind of air?
Cold.
Cold. This one doesn't have a cycle. How'd you know it was convection if there's no arrows?
Because it has heat because of the fire.
Okay, so we see heat, but we know heat has to do with all of them, right?
And heat's going up into the
Yeah, so it goes up.
Okay, so what does that tell us about the density of the air in the balloon compared to the density outside?
That it's like gathering around each other and it's trying to go up. And it's
Okay, what do you mean lighter? What's a more scientific way of saying the air is lighter? Less density, you got it. Same thing here, right? You can see the word density, but how do you know? Even if I didn't have the word density, what gives you a clue that that has to be convection?
Because there's a heat lamp on the bottom.
Okay.
And then when it gets hot, it goes to the top, and when it cools down from the top, it goes back
So
to
you
the
see
bottom.
the rising and falling. Excellent, good work.
Ironing a shirt.
Do we have it? 1 for 1, go ahead.
Burning your hand on a hot cup of coffee.
Do we have it? 2 for 2.
Baking cooks in a skillet on the stove.
3 for 3.
An ice cube melts in your hand.
Did you have any extras that they did not?
Nope.
So exact same answers. Yep. Wonderful. Conduction looks good so far. Radiation group. Who wants to read them? One at a time. Who has radiation here? Okay, you guys are listening to check.
Keeping warm by a campfire.
Got it?
Yeah.
1 for 1.
Microwave oven cooking food through waves.
Yep. 2 for 2.
Sun heating the sand.
3 for 3.
Getting sunburned. Yep.
4 for 4.
Space heater heating a room. Yep.
5 for 5. Any others they did not say? So identical answers? All right. Last group, convection group. You guys are going to read what you had. You guys are checking. Go ahead.
Lava lamp liquids move due to different densities. Yeah.
1 for 1.
Hot air balloon rises when a flame heats the air inside the balloon, making it less dense.
2 for 2.
Heating home in a winter warm, air rises and cool air is pushed back down. Yeah.
3 for 3. Is that all of them?
Yeah.
Did you have any extras? No. Identical answers all around. How do we feel about it? Do we think we did 100%?
No.
Yeah.
Yes.
What questions do we still have about the examples of each that we looked at? Okay, let's review as a class our learning target. What are key words and things we look for conduction? What are going to be the clues that tell us this has to be conduction? Ella?
Direct contact.
Direct contact. If you look at your examples on conduction, all of them should have direct contact. Good. What about convection? What are key words and things we look for? Jillian?
Density.
Density is a key indicator. What else? Alyssa?
Like a cycle.
Cycling, the rising and falling from different things. Good. And lastly, radiation. What key things are we associating with radiation? TJ? Heat waves. Is there direct contact with radiation?
No.
Is there rising and falling currents with radiation?
Nope.
No. And examples that you now have in front of you are ready to be glued down. So with your group, grab a glue stick, glue them down to that poster, and we'll have examples to hang up now as a reminder throughout the rest of the unit. Glue them down. When your group is finished, you may come turn it into the side table, make a pile. When you are completely finished with your poster, you may close your notebook, neatly turn it into the Core 2 crate, and then head back to your seat for our exit pass. We are going to do a quick exit pass Post-it. If you look at the bin at your table, there should be a pack of Post-its. Each person needs 1 Post-it, first and last name, on the back side, so that when it's hanging, I don't see your name. So put first and last name on the back side of your Post-it. And then on the front, you may number it 1, 2, and 3. Name on the back side, 1, 2, 3 on the front side. Okay, before I pull your exit questions up, a couple of quick reminders. Number 1, tomorrow is the deadline. Your 3rd quarter optional extra credit is due by tomorrow. So if you are needing to turn that in, tomorrow is the deadline. Make sure you have it in on time. Friday is Success Day. Any makeup work, missing work needs to be made up and turned in by tomorrow as well. So if you did not get your homework turned in today, if you want to be eligible Friday, that's due tomorrow also. Questions for me before your exit questions? Nicholas? I have told you if you are not. So if you have not heard from me, then you are in good shape for Friday. No other questions? No. Wonderful. I'm going to throw up 3 multiple choice questions. You do not need to write the answer. You do not need to write out questions. Just a letter is fine. When you answer all 3 of them, you're going to come up and put them on the board on our spectrum. You've seen this before, right?
Yeah.
Down here, definitely need more practice. After you answer those 3 questions, if you feel, I'm not sure if I got them right, really not sure if I'm understanding this, I could use another day or another review session about it, you're going to put your Post-it somewhere closer to this end. But if after today you feel, I've got this, I understand it, I could go to my next class and tell that teacher, here's the 3 kinds of heat transfer and here's an example of each, confident, 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 Your Post-it will go closer to this end. Make sense? Wonderful. As soon as you answer your 3 questions, put your Post-it on the board and you are free to go for the day. Have an excellent rest of your day. I will see you all tomorrow.